Hello and welcome. Have you ever stopped to wonder how a single click on a website can somehow spark a coordinated dance between computers all over the world? Well, today we're going to pull back the curtain on that magic. We're diving into 5 foundational concepts that allow these huge independent systems to work together like they're one single entity. So, let's get started.
Here's the game plan for today. We're going to walk through 5 key ideas: middleware, threads, virtualization, the client-server pattern, and finally, code migration. Trust me, each one of these is a critical piece of the puzzle that makes the digital world we use every single day actually work.
But before we get into the details, let's start with the big picture. Just think about it for a second. When you use a service like a global streaming platform or online banking, you're tapping into a network of countless different computers. So how on earth do they manage to work together so seamlessly that, to you, it just feels like one coherent system? The answer starts with an invisible layer that connects everything.
And that brings us perfectly to our first topic, middleware. You can think of it as the unsung hero of the software world. It's this essential, but often hidden, layer of software that acts as the universal glue, allowing different applications to talk to each other, even if they were never built to work together in the first place.
Now, the official goal of middleware is something called distribution transparency, and that's a really powerful idea. What it means is that middleware hides all the messy, complicated details of the network. So for an application, it feels like it's talking to another program that's right next door, even if that program is physically on the other side of the planet. You can imagine how much this simplifies things for developers.
Here's a fantastic way to picture it. Middleware is like a universal translator and a super reliable postal service all rolled into one. Imagine you have 2 programs, written in completely different programming languages, running on totally different machines. Middleware steps in, translates their messages, and makes sure those messages get delivered, allowing them to have a perfectly normal conversation.
So, what does middleware actually do day to day? Well, for one, it manages things like remote procedure calls, which let one program run a function on another machine as if it were right there. It also supports message queues, so apps can send messages to each other even if they aren't online at the same time. And maybe the coolest part is something called interceptors. This allows you to add extra features like security or data backups without ever having to change a single line of the original application's code.
Okay, so middleware is all about connecting different programs. But what about making a single program more efficient and powerful? Well, that's where our next concept, threads, comes into the picture. This is all about learning to multitask within a single application. To really get what threads are, you have to see how they differ from processes. You see, a process is its own little self-contained program with its own private memory. That makes it pretty heavy and slow to switch between. Threads, on the other hand, are super lightweight. They all live inside a single process and share that process's memory. This makes switching between them incredibly fast. But there's a catch. It's up to the developer to make sure the threads don't step on each other's toes and mess up the shared data.
Let's use an analogy. Think of your web browser as a factory. When you ask it to load a web page, it doesn't just do one thing at a time. No, it's smarter than that. It unleashes a team of specialist workers. These are the threads, to work at the same time. One thread starts downloading the text, another one grabs the images, and a third one starts loading the video. Because they all work in parallel, the whole page appears much faster.
Now, this leads to a really efficient design for servers. You have one dispatcher thread whose only job is to accept incoming requests. It then hands off each request to a free worker thread from a pool. But here's the really clever part. Let's say a worker gets stuck waiting for something slow, like reading a file from a hard drive. Instead of the whole server just sitting there doing nothing, the system instantly switches to another thread that's ready to do some work. This keeps the server running at maximum productivity.
Alright, so we've talked about connecting software and making that software multitask. Now, let's zoom out a bit and look at the physical hardware itself. How can we take one really powerful computer and make it do the work of many? The answer is our third big idea, virtualization.
In a nutshell, virtualization is the technology of creating virtual or simulated versions of computer resources. It's the absolute foundation of modern cloud computing because it allows us to take a massive, powerful physical server and neatly slice it up into lots of smaller, completely isolated virtual machines.
So basically, virtualization lets one big server wear many different hats at the same time. It can pretend to be a web server, a database server, and an email server, all at once. Each of these personalities runs in its own little virtual world, and it has no idea that there are others sharing the very same physical hardware.
Now, it's useful to know there are 2 main flavors of this.
First, you have a process VM, like the Java virtual machine. This creates a simulated environment for just a single application, which allows that one app to run on any kind of hardware. But then you have a virtual machine monitor, or VMM. This virtualizes the entire computer, which lets you run multiple complete operating systems, say Windows and Linux, side by side on the exact same machine.
Okay, so we have our building blocks now. We've got middleware to connect things, threads to make them efficient, and virtualization to manage our resources. So what's the most common way we actually organize all these pieces? That would be the famous client-server model.
The restaurant analogy is just perfect for this. The client is you, the diner, who makes a request. I'd like to see the menu, please. The server is the kitchen, which takes that request, processes it, and provides a response. Here is your menu. It's a really simple but incredibly powerful pattern. Clients are the ones who start the conversation, and servers are the ones who respond.
Most modern apps are built using a three-tiered structure. First, you have the user interface tier, which is what you see and interact with on your device. Then there's the processing tier, which contains all the core logic of the app. And finally, you have the data tier for storage. The real genius here is keeping these layers separate. It means developers can update the look and feel of the app without messing with the database, or they can add more processing power without changing the user interface. This modularity is absolutely essential for building big, complex systems that can be maintained over time.
So what happens when you have millions of client requests coming in? You can't just have one server. You need a whole group, or cluster, of them. But how do you make a whole bunch of servers look like one single super powerful machine? Well, you use a very clever trick called TCP handoff. A special switch acts like a traffic cop. It sees all the incoming requests, it quickly picks an available server from the group, and then it literally hands off the connection. From that point on, the client talks directly to its assigned server. It's a beautiful way to distribute the workload without the client ever knowing what's happening behind the scenes.
And for our fifth and final concept today, we're going to explore a more advanced idea, one that kind of flips the whole traditional model on its head. Instead of always moving data around, what if we could move the program itself?
This leads to a pretty fascinating way of thinking. Imagine you have a massive database. Those are your raw materials. Now, the traditional way is to ship all those terabytes of data across the network to your program, your factory. But what if instead you could ship your small factory to where all the raw materials are stored? You know, it's often way more efficient to send a small bit of code to a huge data set than it is to do it the other way around.
Now, this idea comes in two main flavors. With weak mobility, you're just sending the program's code to a remote machine to be started from the beginning. A classic example was the old Java applets that your browser would download and run. Strong mobility is the really wild idea. It's moving a program while it is already running, along with its entire memory and current state. This means a program can literally pause itself, move to a completely new computer, and then pick up right where it left off.
And there you have it. That brings us to the end of our tour. Let's just take a moment to quickly recap the 5 core concepts we've explored today.
We started with middleware, the universal translator for software. Then we saw how threads act as multitasking workers inside a single program. We learned how virtualization lets one computer wear many hats, and how the client-server model provides that fundamental request-response pattern for everything. And finally, we touched on code migration, the advanced strategy of moving the program to the data.
These 5 concepts, really, they are the pillars that our entire modern digital world is built upon. So I'll leave you with one final thought to ponder. As our systems get more and more complex and more decentralized, which of these fundamental building blocks do you think will be the most critical in defining the future of computing? Thanks for watching, and see you in the next session of this